Chapter 16 is a very important chapter. It's about the body surface area and pediatric calculations. Whenever we're calculating the body surface area of a person in meters squared, we take their height in centimeters times their weight in kilograms, divide it by 3,600, then take the square root of that, and that would be how many square meters of surface area their body would have. If you know the height in inches, which we typically would know that, we would know our own height in inches and our own weight in pounds. Multiply those together, then take the division or divide it by 3,131, then take the square root, and that will give you also the body surface area in meters squared. So if we are trying to calculate the body surface area of a child that has a height of 105 centimeters, which is about 42 inches, and a weight of 31 and 8 kilograms, which is about 70 pounds, since we have both metric measure and we have both English measure, let's look at what the surface area would be. If we take the centimeters times the kilograms, we get 3,339. We do the division, get 928 thousandths, then take the square root, and we get 963 thousandths meters squared. We round that to hundredths, and we get 96 hundredths meters squared. Now, if we do the same calculation for the same child, except we use our English system of measure, we would take our height in inches, 42, times our weight in pounds to get 2,940. Divide that by 3,131 to get 939 thousandths. Then take the square root and then round to the nearest hundredth, and we get 97 hundredths. So we have 96 hundredths meters squared using the metric measure, and we have 97 hundredths meters squared using the English system. So you can see that that is close. Notice that the increments of measurement and the spaces on the body surface area nonogram are not consistent. So be sure to correctly read the numbers and the calibration values between them. So instead of using the formulas that we have a table that we can use that will give us the body surface. So we have to be careful to verify for safe dosage. So when we verify the safe pediatric dosage based on the body surface area, we want to determine the body surface area in meters squared. Then we want to calculate the safe dosage based on BSA. That's milligrams per meter square by meter square. So that's some amount of milligrams. Then we want to compare what is the ordered dosage to what is the recommended dosage. And then we want to decide if that dosage is safe. So if the dosage is safe, we calculate the amount to give and administer the dose. And if the dosage seems unsafe, we want to consult with the ordering practitioner before administering. the dosage that you might be given would be in milligrams per meter squared, micrograms per meter squared, grams per meter squared, units per meter squared, or milliequivalents per meter squared. So these would be the standard units of medication given. So let's say that you have a child that is 126 centimeters tall and weighs 23 kilograms. The order is on Conivin, 1 8/10 milligrams IV at 10 a.m. And we want to know if this is a safe dosage. The recommended dosage is 2 milligrams per meter square of body weight. So what we have to do is figure out what this child's BSA is. So we use the formula. We multiply the height times the weight, both metric. So we're dividing by 3,600. Then take the square root. And the child is 9/10 milligrams, or 9/10 meters squared. So we calculate the recommended dosage by taking milligrams per meter squared, which is 2 milligrams per meter squared, times the child's BSA. We get 1 8/10 milligrams. And we decide if the dosage is safe. So the dosage ordered was 1 8/10 milligrams, and 1 8/10 milligrams is the amount recommended by the BSA. So we go ahead and calculate and administer one dose. Now, in order to calculate these problems, the first thing we do is we convert. So if we were given English measure and metric measure, we would have to decide and change them so that they have this. We're using kilograms for weight and centimeters for height, or we're using pounds for weight and inches for height. So we have to keep within the same units of measurement. In step 2, we have to think, are we going to give more than 1 milliliter, or will we give less than 2 milliliters? So we try to think about that to see what would be a reasonable dosage before we begin. So the calculation using the proportion method would be 1 milligram is to 1 milliliter, as 1 8/10 milligrams is to how many milliliters. And when we do cross products, we get 1 8/10 milliliters. Now, if you like the desired divided by the half times the quantity method, then what is desired, or what the doctor ordered, is 1 8/10 milligrams. What you have is 1 milligram, and the quantity is 1 milligram. So milligrams cancel out, and you have 1 8/10 milliliters. So remember, there are two ways to calculate: the ratio and proportion method or the formula method, and either way is appropriate. Now, this is what the IV might look like. Here's your clamp, an injection port, the cap needle, the check valve, the drip chamber, the drug fluid. We have a clamp here and another injection port. When mixing IV drug solutions, the smaller the added volume, the stronger or higher resulting concentration. So it's called minimal dilution. And the larger the added volume, of course, that means you are diluting it more, you're making it weaker, you're lowering the concentration, so it's called a maximal dilution. Alright, so let's review. So the volume control sets have a drop factor of 60 GTT over per milliliter, and the total volume of the medication, the IV dilution fluid, and the IV flush fluid must be considered to calculate the flow rates when using volume control sets. We have a caution: an exceedingly high concentration of an IV drug can cause vein irritation and potentially life-threatening toxic effects. So dilution calculations are critical skills. So we'll use this formula to calculate the daily rate of pediatric maintenance IV fluids. 100 milliliters per kilogram per day for the first 10 kilograms of body weight. Then 50 milliliters per kilogram per day for the next 10 kilograms of body weight. So 100 milliliters per kilogram per day for the first 10 kilograms of body weight, or 50 milliliters per kilogram per day for the next 10 kilograms of body weight. So the first 10 kilograms gets 100 milliliters, but then the next 10 gets 50. So we'll use this formula to calculate the daily rate of pediatric maintenance IV fluids. So let's say that you have 20 milliliters per day, 20 milliliters per kilogram per day for each kilogram above 20 kilograms of body weight. So 20 milliliters per kilogram per day for each kilogram above 20 kilograms. So what we have to know is how much the child weighs 24 kilograms. So if you get 100 milligrams per kilogram times 10, that's 1,000 milliliters. That's for the first 10 kilograms. So now we have 14 kilograms left. Well, the next 10 gets 50. So 50 times 10 is 500. So now we have 4 kilograms left. The next 4 kilograms gets 20 milliliters per kilogram per day. So that's 80 milliliters. So we have to take the child's weight and we have to break it down into increments. The first 10 kilograms of weight is 100 times 10. The next 10 is 100 times 50. And then the leftover 4 times 20. So that's 1,580 milliliters per day. So how much do you give per hour? So this is how much you give over a 24-hour period. So you would be rounding to the nearest whole number. So you would give 66 milliliters per hour. Now, a red flag should go up in your mind if either plain 5% dextrose in water or 9/10% sodium chloride is running continuously on an infant or a child. So you need to consult the ordering practitioner immediately. In Chapter 15, Intravenous Solutions, Equipment, and Calculations, we're going to look at some abbreviations that are used um, with giving IVs. The D stands for dextrose, the W stands for water, S stands for saline, NS is a normal saline solution or a 9/10% NaCl. NaCl is sodium chloride. RL is a Ringer's lactate, and LR is a lactated Ringer's. Hypotonic means used to dilute excess serum electrolytes. For example, 4,500% saline. And an isotonic is used to expand volume and maintain normal tonicity. So an example of that would be 9/10% saline with a lactated Ringer's and a 5% dextrose. Hypertonic is used to correct electrolyte imbalances. So an example would be if you had 5% dextrose and a 9/10% saline and a 5% dextrose and a lactated Ringer's. Your IV sites can be peripheral, which is where the rate of infusion should not exceed 200 milliliters in an hour, or it can be central line, which accommodates larger concentrations and volumes of fluid. The complications you can have from IV sites are phlebitis, which is blood clots, infiltration, and infection. So here's what an IV bag might look like on a stand. So here's the bag. Here is an injection port where you could give other medication like antibiotic. The drip chamber is here, and then the roller clamp, and that's where you regulate how many drops over a period of time that the patient would get. This is called an IV piggyback, and this is used sometimes if you want to add medication, but you don't want to add it into the saline solution. Also, sometimes if you're giving blood to the patient, you might have that separate. So IVPB means IV piggyback. So you have a different medication given with the normal saline bag. The IV flow rate is ordered by the physician, and it's the nurse's responsibility to regulate, monitor, and maintain the flow rate. So the IV flow rate is in milliliters per hour. So you would regulate an IV volume by electronic infusion pump or a controller calibrated in milliliters per hour. So total milliliters ordered by the physician over the total hours ordered. And we abbreviate that as ml over H, and we round that to the nearest whole number. So let's say that the doctor ordered D5W250 milliliters IV over the next 2 hours by infusion pump. So the first thing you're going to do is to think 250 milliliters is to be infused in 2 hours. So how much will be infused per hour? So remember, we set up the ratio as the amount ordered over the time in hours. So the total milliliters ordered, which is 250 milliliters, over 1 hour or 2 hours ordered. And when we reduce that, we have 125 milliliters per hour would be how you would set up the pump. So the IV flow rate in milliliters per hour is the infusion rate. But if it's less than an hour, then we have to look at it in terms of minutes. And we know that 60 minutes is 1 hour. So we still are dealing with the total amount of ordered, but now it's over minutes. And then we're changing minutes into hours, so we still have milliliters per hour. So let's say that your doctor ordered ampicillin 500 milligrams IV in 50 milliliters D5NS in 30 minutes by controller. So we're looking at the amount of medication, 50 milliliters, and the time is 30 minutes. So we set up what the doctor ordered, 50 milliliters, the time in minutes, which is 30, but then we have to change minutes into hours. So remember, what you want to get rid of has to go opposite of what you have. So I have 30 minutes in the denominator, so it is 60 minutes in the numerator. So the minutes cancels out, and you would have, after this reduces, 100 milliliters per hour. I am not going to give you guided notes over this lesson, and I will not have problems on chapter 15 on your exam. However, I did want you to see what an IV solution looks like and how you would go about calculating the dosage.